tiny 3D printed combat robots are taking the world by storm. These little machines are a ton of fun to build and even more fun to compete with. And in this video, I'm going to go through some of my top tips for building these little machines that I've learned over the last few years, because let me tell you, it's a bit of an arms race. Let's get started. How's it going, guys? Angus here from Maker's Muse, and this is Dead Cat Bounce. It's one of the newer versions of it. This tiny robot weighs 150 grams and fits into the Australian Ant-weight robot combat class. But don't let its tiny size fool you. Ant-weight combat robots are incredibly destructive, and in fact, they provide some of the most exciting robot matches I've seen to date. While it's true that they might not be as impressive as the massive battle bots you see on TV, insect weight class combat robots are incredibly accessible, affordable, and fun to build, and you don't need a fully fledged workshop to do it. I've made many videos on building these combat robots over the years, and I'll continue to do so, but I thought it'd be nice to put together a series of just tips that can help new builders get started and avoid the pitfalls that I fell into when I was getting back into this hobby. Because at least here in Australia, building these tiny Ant-weight robots has become a bit of an arms race. In just 2 short years, we've gone from machines that did barely any damage to machines that would literally hit each other off the roof repeatedly for 3 minutes straight without breaking. But without further ado, let's get stuck into tip number 1. Don't pocket your CADs because infill is lighter. Now, this is a pitfall that if you're from an engineering or industrial design background, you're probably going to fall into, because you'd think if you're making a part and you want to make it lightweight, well, you would add pockets, which if you're machining the part would remove material, therefore make the final part weigh less. But when you're 3D printing these things, a pocket in the design actually means you're adding perimeters, and those perimeters will actually end up being heavier than if you just left it solid and the internal of the part was actually filled with just infill instead. The ability to have a part with a sparse infill is actually an incredible superpower that only FDM/FFF technology can do. Other technologies, you have to model in your own infill matrices and lattices and that sort of thing. But with FDM, you can just choose what kind of infill type you want, what sort of percentage you want, and then it'll actually just create it in the G-code for you. And it is incredibly powerful for fine-tuning the ratio of strength to weight for your 3D printed part. And obviously, because these machines weigh nothing, like you want to keep the weight as low as possible, you generally want to use a sparse infill and a fairly low perimeter count to keep the part weight down. But in areas that you want extra strength, well, then you can actually use modifiers. Modifiers are really powerful, but they can be quite confusing to understand. So I've made a whole tutorial video which goes over how to model your own modifiers and use them to create parts that have the perfect balance of strength to weight. My next tip is on clearances. Add them, and add more than you think. When you're modeling in the software, everything looks perfect. You know, it looks like everything lines up nicely. It looks like the battery was slotted in nice and snug, and it's perfect. Then you print it and you go, oh, the plug doesn't fit. Oh, the wiring is too large. You want to add more clearance than you think and the design stage, and it takes practice. I get it. Even when you're in the CAD stage, that CAD mindset, things can look huge when they're actually tiny. But when you come to the real world, well, 3D printers aren't perfect. They're not perfectly accurate, and at the end of the day, you're melting plastic through a 0.4 nozzle anyway, so you're going to want to add clearances so parts have some wiggle room and you can assemble the thing properly. Because let's face it, this thing's going to be bashed around the arena and damaged and possibly destroyed, so you want to make sure there's a bit of wiggle room between the parts if anything takes damage, or you might not even be able to get the top cover off again. My next tip is the designing stage of the robot, and that is to use reference CAD models if you can. There are reference CAD models freely available for pretty much every standard combat robot part on the planet, be that gear motors, batteries, or speed controllers. And you can just grab these files, drop them into your CAD program of choice, and then use that to design the robot around it. Now again, make sure you add a lot of clearance because you'll need it. The real world isn't perfect, but this can make designing the machine really easy. You don't have to use reference CAD models because, for example, a drive motor will just have a footprint you can model in just manually using measurements. But using the reference models in your CAD can be really handy to avoid part conflicts that might only become apparent when you're right at the end assembling your machine. You realize, oh, the gear motor actually intersects where the weapon blade is, and the robot doesn't work. My next tip is very hard learned, but unfortunately, don't use threaded inserts. They don't work. Threaded inserts are incredible. I use them on so many different projects, but they simply don't work with combat robots, and there's a few reasons why. The first reason that inserts suck for combat robots is most people would print their frames out of a TPU, whether it's a really soft TPU or a more semi-rigid TPU. These TPU filaments do not hold on to the threaded inserts in big impacts. Case in point, this is the old frame for Dead Cat Bounce printed with a 64D TPU and the threaded inserts pulled out. Even though I couldn't pull them out by hand, the forces in combat are so great that they just rip out. Now, there's a few ways you can get around it. Some people insert the threaded inserts from underside and therefore it has to pull through the plastic. But in combat, I've had them just bust through the side of the TPU anyway, because they're quite sharp, they create a sort of stress point. And the final point against using threaded inserts, they're brass. They're very heavy when it comes to a tiny machine like this, where every gram counts. They add up. And if they pull out and they're heavy, they're not very good, are they? So what are the alternatives that work better? Well, successful combat robot builders will do one of the following. They'll either bolt through the entire frame in a sandwich-like construction using a long, thin M2 bolt, for example, that will go all the way from the top plate through the frame to the bottom plate into a nut. Therefore, there's nowhere that screw can go unless it literally sheared in half or the whole frame got destroyed. Or they'll use a long bolt into a really small undersized hole and literally just squish the threads into that TPU. That's been used by several builders very successfully. Or personally, my new favorite is to use standoffs instead of threaded inserts. I bought these M2 standoffs online. They're aluminium, they weigh very little, and they have an M2 thread that's tapped right through the thing, or at least mostly into it. And that means I can have this inserted into my TPU frame and the top and bottom plates sandwich onto it and bolt through into that insert. I don't know if this is going to be heavier or lighter than just a long M2 bolt, but it makes serviceability a lot easier, and so far it's held up really well. My next major tip is to design for assembly as well as repair. So when you're putting your robot together, you really want to be mindful of how the parts assemble, and especially how that little wiring loom is going to be put together, because when you solder stuff together, you can't just pull it apart. And for example, if your weapon motor threads through a hole in the frame and then solders to that board, that's going to make assembling it quite difficult because you have to solder it into place with it threaded through the frame. So consider an alternative. Instead of a hole, you just have a channel. This channel is constrained by the top plate, so when everything's in place, those motor wires can't move. But if you need to repair anything, you can take that top plate off, and then the entire assembly can be lifted clear of the robot for ease of access and soldering and repair. Being mindful of how stuff is actually put together and how stuff will be repaired is something that just takes time, and it's something to think about when you're in the CAD stage, when you're putting stuff together, like, oh, this motor wire actually will have to run across the weapon motor to get to the other side where the speed controller is. That's going to not work, that's going to be too difficult. Maybe I can just move where the speed controller is or where the inputs are to make it a little bit more accessible. And again, I really recommend against having wires running through holes in the frame. I don't recommend doing that. I recommend channels instead. If you can avoid doing holes, it'll make your life a lot easier when it comes to repairing your machine. Next tip, shock mount everything. Do not rigid mount delicate components to your robot's chassis, because in impacts, those shock forces will go straight through to the delicate components and they'll break your control boards, they'll break your motors, they'll break everything. Shock absorption is the key to robot combat success. In my recent videos, you've seen my robots bounce off the roof, be hurled around by much more powerful machines, but my robots come back for more. And that's because I've built robots with TPU frames that can flex and absorb impacts, but also because I don't rigidly mount anything in my machines. I put the drive motors into slots and they're constrained by the top plate. I have a cavity where the speed controllers are and the battery is, but none of that is rigidly mounted. It's mounted in such a way that the wires won't get snapped or fatigued in a big impact, but they're not rigidly mounted, and that is key to a robot surviving large impacts. You must make sure that those impacts do not transfer straight into delicate components. Do not rigidly mount anything to the frame. Make sure everything can move just a little bit with a bit of shock absorption, and your robots will be so much more durable. And the next tip for this video, air armor is better than any other material for protecting your robot. If your opponent can't hit you, they can't do damage. You can employ the concept of air armor a few different ways, but the idea is simple. If your robot is hit, then it's going to just go through air and not hit anything vital, and you can keep going. So for example, if your robot's made out of TPU, don't make it out of really thin TPU walls, because they'll just get pierced and then go straight into a delicate component like a battery. Instead, make it pillowy and large, but very, very low infill. So if that wall is pierced, it's very unlikely that the blade is going to continue all the way to the innards of the robot. Instead, it's likely to just grab on the outside of that armor and fling your machine away with a sizable gash, but no actual damage. You can be really creative with the concept of air armor. I've seen people employ keep away sticks and thin plates that stop their opponent from being able to hit them at all, but they are generally a case by case basis. But again, the idea is simple. If your opponent can't hit you or hit anything delicate, then they can't knock out your robot. If you want even more tips on improving the quality of your 3D prints, then maybe considering checking out my ebook, The Ultimate Book of 3D Printing Tips and Tricks. This book expands on many of the concepts I've talked about in this video on how you can improve your 3D prints, and they are very applicable to making better 3D printed combat robots, and you can check it out in the video description below. So that concludes part 1 of my tips on building tiny combat robots with 3D printing, but I'd love to hear your thoughts in the comments below on what tips that you have for improving the reliability and printability and serviceability of your combat robots using 3D printing, because I'll definitely take some of those ideas and tips and roll them into the next episode in this series. Thanks for watching, guys. Bye.